in this lecture we will discuss about the universal Turing machines and linear bound automata with some examples. We will see some examples of linear bound automata and what is the Turing machine first, then what is the linear bound automata. This linear bound accept this context sensitive language is accepted by the linear bound automata. How this is accepted, we will check to that. So, now we have to come to the universal Turing machine, or all of we know these tuples, 7 tuples are there Turing machines. So, what is universal Turing machine? What is the universal Turing machines? So, this is a programmable machine which simulate other Turing machines. So, this a universal Turing machine is a Turing machine that simulate arbitrarily Turing machine on arbitrarily input. The universal machine essentially achieved by reading the both description of the machine to be simulated as well as the input to that machine from its one tape. So, its own tape. So, this main definition is programmable machine which simulate any other Turing machine. So, what is the meaning of this? If any universal, suppose we have some Turing machine, suppose we have Turing machine M1, Turing machine M1. So, this is a Turing machine, this is, so this is a Turing machine M1, suppose Turing machine M1, then Turing machine and string is W1. So, like that Turing machine, another Turing machine this is another Turing machine M2 and string is W2, like that some Turing machine it is given. So, what is the universal Turing machine is that universal Turing machine is a programmable machine which simulate any other Turing machines. So, all the Turing machine can be simulated by the universal Turing machine. So, universal Turing machine is like that, suppose M, W, this is a universal Turing machines. So, for this you have to, you can take here, means you can take here input as a U, you can take as a M1, W1. Similarly, you can allow to take M, M2, W2. So, all the, if it is a universal Turing machine, it can simulate all the Turing machines. So, you have to take the machine. So, you can say this is a combination of all the machines, it is programmable machine which simulate any other Turing machine, whatever other Turing machine that can be simulated by the universal Turing machine on its own tape. Here is the M1 and W1 is the, M1 is a Turing machine which simulate W1 and also that can be simulated by the universal Turing machine. So, U is the universal Turing machine, you can write universal Turing machine, UM is the universal Turing machine. So, here we have to know, do not take the universal Turing machine, you have to take the machine with some input string, machine whatever Turing machine with input string. Similarly, this universal machine can simulate here machine 2 with W2. This suppose some string is accepted by the Turing machine 2 and that can be, you have to take that machine and take the strings whatever accepted, that can be accepted by the universal Turing machine, universal Turing machine. So, next what is the linear bound automata? Linear bound automata. So, this linear bound automata is nothing but it is a Turing machine. So, Turing machine already we know, sir, our end position of when we will take the string on the tape and tape could be go to the finite, tape could be go to the infinite. So, here we have to, what you have to do, we have to fix the end point of the tape, then this is a linear bound automata. So, it could not be go to infinite. Suppose here we can go to, suppose here a string is given. So like that, suppose A B, suppose B, like that string is given and both side is blank is there in normal standard Turing machine. So this linear bound automata is a Turing machine. First of all, think that this is linear bound automata is a Turing machine, but this is a different kind of Turing machine. So this in standard Turing machine there is no tape limit. You can remove this blank as some input alphabet and goes to infinite. But here linear bound automata we have to fix the both end. So tape ends should be fixed by the bound. Bound means you have to, this one will be end of the, this one is the end, left end, and this one is the right end, this one is the right end. So whatever operation, whatever computing will be done in between left and right end. So you could not, your tapes you could not go to infinite. So this is allowed only whatever left end right end is there, you have to fix on that. Whatever all the computing will be done in between left end and right end. So there is no infinite, position you can move to the tape like the standard Turing machine. So here Q is a finite set of states, tau is the same thing, is the input alphabet, tau is the tape alphabet, and this is the sigma is the input alphabet, and this is the Q0 initial state, ML, this is the ML is the left end marker and MR is the right end marker. These two is new, these two, and del is the transition function, same with Turing machine, F is the final state. So we mark the left end and right end. So tape is fixed for you and we have to compute on that tape only. You cannot go to the take your tape to infinite. So this is the linear bound automata. This linear bound automata, whatever we have, if some language is not context free, then the language is a context sensitive language. So using pumping llama we can prove a language is not context free. If it is not context free, that cannot be accepted by the push down automata. We have to go to the higher machine. Higher machine means that is the linear bound automata, and you can go to the after linear bound automata you have Turing machine like a recursive language, then recursive enumerable language. These are be accepted by the Turing machine, later we will check on. So now you see you we have a language is given and your Turing machine has fixed the tape, and in between the tape we have to compute. So take a context sensitive language, how this is accepted by the linear bound automata, how this is accepted by the linear bound automata. So let us take on context sensitive language. So here L is, we can take, already we have done this one in class, A n, B to the power n, C to the power n, n is greater than equal to 1. Suppose this is a context sensitive language, you can say here this is not a context free, because at a time two comparison, A is comparison with B and A is simultaneously comparison with C. So this is a not context free language, we can prove it by using pumping llama. So now we have to go for the higher machine, that is linear bound automata, linear bound automata. So here we know already linear bound automata, that is a Turing machine. So you have to take this Q0 and this is what you have to do, this is A and this is X and right. So now this is a Q1. So what you have to do for X, for A, if first A you have of the tape you have to replace by X and move right, then Q1, then Q1 is here, for all A you move right and keep as it is A, then Y R, then B R, B, this is Y R, B Y R, this is B, for at a time 1 A, 1 B, 1 C you have to replace to X Y Z, X Y Z. So this is y, this is y r, then this is what you have to get here, this is after this you have to find here b, b r and z, z r, then c, c to z and left move, and suppose this is q2 and this is q3. So you see what you have to do here. Suppose a is replaced by x, a is replaced by b is replaced by y, and c is replaced by z. C is replaced by z. You have to take these three. A is replaced by b, and C is A is replaced by x, B is replaced by y, and C is replaced by z. So erase this. So now you have to check it. So Q3, you have to make a loop here. Again you have to go to initial state. First one A replaced by x, one B replaced by y, one C replaced by z. Then after go back to initial state. So now Q3, what you have to, when you will back to A, what you have to get? So here you will get here all A2, AL and B2, BL and Z2, ZL and C2, Y2, 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 YL, YL. So when you will find here x and A, B, Z, Y, when you will find here x, then go to initial state, x, then x, this is right move, then after you have to here, this is y, y2, yr, then this is y2, yr, then z2, zr, then this is q4 and q5 is final state. This is blank and blank r. This is the final state. So we'll check how this is accepted by the linear bound automata. How this is accepted? We have designed this Turing machine, then we have to prove it how this is a linear bound automata. Suppose take a string 2a, 2b, 2c. Let us take a string 2a. In TAFE we have 2a, 2b, 2c, 2b, 2c. So what will be there? Your tape is bound now. You cannot move here. This is the fix and this is the fix. This is left marker ML and this is the RL. So mark MR. This is MR. Mark right. So we fix this both end. We cannot move to that area. So whatever computation will be done in between this only. So now you check it, when Q0 A to x, then A will be replaced by the x. A will be replaced by the x. Now this is x and this is A, then B, C, then C, then blank. So now Q1 point to A. Clear? So now Q1 is point to A. If A is there, just you have to move right in Q1. So what will be there? So it will be, what will be there here? So now you see, this is x and this is A and this is B and this is B and this is C and C, like that C. So, now Q1 point to B, Q1 point to B. Now, if Q1 B is there, where you have to go? Q2, and this will be replaced by Y and go to right, replaced by Y and go to right. Now, you see this is X and this is A and this is B will be replaced to Y and this is B and C, C. Now, this is right, this is go to right. Now, Q3 will be point to Q3 will be point through. So, this is why this is not working. Q3, Q3 point to B. So, Q3 point to B. Now, you see if Q3 point to Q2, this is Q2, Q2 point to B. Now, Q2 point to B, Q2 point to B, you see B is there, then move right, B will be remain same, then move right. So, what will be there? So, here you see here what will be there? This is A, then sorry, this is X and this is A, this is Y and this is B and this is C. Now, C will be Q2, now point C, Q2 point to C. This will be Q2, Q2 point C, Q2 point C. Now, Q2 point C, what will be there? If Q2 point C, then C will be replaced to Z, then C will be replaced to Z. You see here what will be there? C will be replaced to Z. So, now this is X, this is A and this is Y and this is B and this is C and this is Z. C, so this is Z and this is C, Z, C. This one is C will be replaced to, now this Q2 you have to left back. So, you want to replace Z, this Q3 will be point to B. So, like that it will be left, it will come to the X. When it will be X, again Q0, the see here 1 A is replaced to X, 1 Y is replaced to B and 1 C is replaced to 1 B is replaced to Y and 1 C is replaced to Z. So, similarly, in Q3 you see A is left move, B is left move, Z is left move, Y is left move. So, left, you can go to the X. When in find in Q3 X, you have to take a right turn. When you right turn, you will find here A. Again A will be replaced by X, then B will be replaced by Y, then C will be replaced by the Z. So, like that it will be replaced equal number of A, equal number of B and equal number of C. So, then you can compare that. So, after completion of all replacing X, Y, Z, then you see in Q3 you will be Z, Y, you have to move left, then when it will X, it will be go to Q0. If Q0 all A and B, all C are replaced by the X, Y, Z, so you could not find A, so what will be there? You must have to take a transition from Q0 to Q4, Y to YR, Y to YR. When Y, if X is after A is not there, means you have only Y is there, after X you have Y. So, Y you have to take a transition to Q4, then Q4 blank right, Q4 all YZ there is a loop, then after when you find the blank, string is accepted. So, means here we fix the bound tape. So, we do not require to move left side infinite or right side infinite, it will be fixed the both end. That is why this is a linear bound automata, this is a linear bound automata. So, now see some question, this question come in a net exam. So here one question is given, so we can see what would be the answer, we can see what would be the answer. So here is the 4 option is given, so what would be the answer? So we can check it, you see here Q0, you can draw the diagram, this is Q0, Q0, you see here Q0 all A, this is A, then Q1, and this is A to right, A right. If A is there from Q0, read it and move right, and B also, if B is there from Q1, Q1 B read and move right. Then after this is Q2, in Q2 A is there, then there is a loop, A is there, then A to AR, then this is Q2, and see Q2 A is there, okay, A is there, then move right, then Q3 B is there, Q3 there is a Q0, Q1 to Q2, Q1 to A, and this is Q3, this is a Q A B Q2 R, and this is a Q3, this is a Q2, this is a Q2, and Q2 B, this is a Q2 B2 and Q3, this is a B B R, B B R, this is a B B R. So it is mistake, this is Q2, Q2 B to Q3 B R. Now Q3 you can say this is a accepted state, and you check it A B A star B. So what is the accepted here? A B A star B, A B A star B is accepted. Now see Q0 A is there and read A, go to Q1, and Q1 B is there, read B and go to Q2 and move right, and Q2 A read and keep as it is as A and loop is there, and B in Q2 B is there and read the B and keep as it is and move to right, then Q3. So we can say this is the option C is the right answer. So if you will assume this is Q3 as a final state and Q0 as a, you see here it is written Q3 as a final state and Q0 as a initial state, Q3 as a final state. So this is the option C is the right answer. So it is given that linear bound automata, what is the linear bound automata is a finite automata, Turing machine, push down automata, none of the mention. So linear bound automata is which one? So option you can say linear bound, is it a finite automata? No, it is not a finite automata. Is it a push down automata? No, it is not push down automata, because it accept only context sensitive language, that context sensitive language cannot be accepted by the push down automata. So here you can say this is a Turing machine is the right option. So here you can say Turing machine is the right option. So now we have, so see another questions. So given a Turing this one, so already we did this one, this is question number 3. So L1 is a regular language, L2 is a context free language. So L1 union L2 can be accepted by. So here you can say what is the right answer. So is it deterministic automata? So no, it is not a what is the first you have to find? So what is the L1 and union L2? So already I discussed in this closure properties of context free language, L1 union L2, this is accepted, this which language will be generated. This L1 is a regular language, union L2. So this is always higher language. If you take this is a regular language and this is a context free language, so you can say union of regular language, union context free language, or regular language intersection context free language will be always always higher, always contest free, always contest free language. So, if it is a contest free language, then it is it could not be you see it is it accepted by deterministic finite automata? No, it is not accepted by the deterministic finite automata because this is a contest free language. Is it accepted by the linear bound automata? Yes, it is accepted by the linear bound automata, but this is not why linear bound automata. I discussed that this automata, linear bound automata will be accepted context sensitive language, but here context sensitive is higher language. This is the context sensitive is higher language. So, this is the LBA, linear bound automata. So, this is a push down automata and this is a finite automata. So, if any language, regular language is there, that can be accepted by the finite automata, that can be accepted by the push down automata, that can be accepted by the linear bound automata. So, similarly, if a context free language is there, that can be accepted by the push down automata and also that can be accepted by the linear bound automata. So, but if a context sensitive language is there, that cannot be accepted by push down automata or not either push down automata or finite automata. So, this is a Venn diagram you can see, that is why answer is the linear bound automata. So, regular language also accepted by the Turing machine. It is accepted by the finite automata, it is accepted by the push down automata, also it is accepted by the Turing machine, which is the higher machine that can be computed all the language. Means Turing machine is the higher machine that can be computed all the language like regular, context free and context sensitive. So, all the language recursive, enumerable, all language will be accepted by the Turing machine. So, these are the reference books. So, you can use any book like that, Michael Sipser or Ullman Hofkrath. So, this is I also discuss some MCQ, and this topic you will find the maximum number of theory type of questions in GATE exam and NET exam. So, thank you so much.